Welcome to Regulated Power Supplies Part 12. All right, so here is our power supply that we've developed so far. And we've got the variable voltage, we've got the op-amp regulation, we've got this one has the fixed current regulation or limiting, where it limits at a specific high current. Ours was at 0.583 amps. With the output shorted, this power supply will run up to 0.583 amps and then limit itself and not destroy itself. So this next part, though, we want to design a circuit that gives us the ability to vary the current limiting. So just like we're varying the voltage, we'll be able to vary the current limiting. All right, and here is our circuit. You can see that the fixed current limiting diode branch has been replaced now with the 5088 transistor Q4 and another variable resistor, a 5K variable resistor RV2, an R6, and the R5. All right, so in order to start breaking down the circuit and calculating values for the circuit, we need to imagine as though the variable resistor RV2 was turned all the way to the position where the base of Q4 is now electrically connected to the emitter of Q1. Okay, now that we're in that position, this is going to be our I out min position, so our minimum current position. And you can see that the VBE of the transistor when we're in this position, when VR5, the voltage VR5 starts to come up, current goes up, VR5 starts to go up, that when that VR5 hits the equivalent voltage of VBE of Q4, that transistor will start to bias on and it'll effectively rob current from the base of the Darlington pair. And that's how the current limiting is done. So if we've got that, if we know that VR5 is equal to VBE of Q4, then that would be equal to 0.7 volts. Now, we can choose our I out min. What do we want to be able, what's our minimum current that we want to be able to regulate? And for this example, we're going to choose 0.1 amps. If we divide the VBE of Q5, the 0.7 volts, by our I out min, that gives us an R5 value of 7 ohms. Okay, now that we've defined our minimum range, and we found our R5 value of 7 ohms, we want to imagine that we're going to turn that RV2, the 5K potentiometer, all the way to the position where the base of Q4 is now connected electrically to R6. And that is going to represent our I out max position. So before we've always chosen for this example 0.5 amps for our max current. That's where we want to be able to physically operate at. So we want to choose an I out max, a regulation current of something above that. Give ourselves, like we did in the previous one, give ourselves a little bit of padding, and let's choose an I out max of 0.6 amps. So if we do that, we know that if we've got an I out max of 0.6, that current is basically flowing through R5. That VR5 now is that 0.6 amps times 7 ohms. And so that gives us a VR5 of 4.2 volts across R5. And you can see that the RV1 and R6 are physically in parallel with that VR5. So now that we know that there's 4.2 volts across that R5, it's also going to be across the variable resistor and the R6, that branch. So if the potentiometer is all the way to the R6 side, we know that VR6, when that transistor starts to bias on, will be 0.7 volts. It'll be equal to the VBE of the Q4. So if I've got 0.7 volts across R6, then I must have across the RV2, the potentiometer, I must have the rest of that voltage. So the 4.2 volts minus the 0.7. So now I've got a VR2 voltage of 3.5 volts. So now that I've got the VR2 voltage of 3.5 volts, which is VR5 minus 0.7 of the VR6, we can find the current through that branch, through the potentiometer branch and the R6. And so IRV2, the current through the potentiometer, is equal to the VRV2 divided by the RV2. So 3.5 volts divided by the potentiometer is rated at 5K, so divided by 5,000 gives us a branch current of 700 microamps. Now that we've got that, we know that that's equivalent to IR6, that branch current. We can divide the 0.7 volts by the 700 microamps, and we solve for an R6 value of 1K ohms. So to calculate the power for R6, we're going to do V squared divided by R. We know the voltage is 0.7 volts. Square that divided by the 1K ohm, and that gives us 490 microwatts. Not much power for that guy. For PR5, though, that's another story. We've got, let's go ahead and use our I squared R. So we want to use our current, our max current, which is going to be 0.6 amps squared times our 7 ohms. That gives us a 7.52 watts for our set R5. Okay, so here is our final schematic with variable current limiting. So we can limit our current all the way from 0.1 amps to 0.6 amps. Here are the parts looked up from Mauser. And you notice with the variable current limiting, our R5, the power in that position, because the resistance went up a little bit, we end up with more power in that position. So it's a 2.52 watt resistor. The problem is you really need to double the power rating for that resistor. So I looked up and found a 7.5 watt resistor, 7 ohm resistor. Now the thing is, you can see right there the R5. This is what it looks like. You can see the price difference. So all of a sudden we've got a $4.21 part there to dissipate that power.